In my previous video I talked about these things, right? That the displacement as a function of time of a simple harmonic motion is given by this, and if you differentiate it you'll get the velocity, and differentiate it again and you'll get the acceleration. Okay, so I talked about these and the time period of oscillations as well. So in this video I'd like to talk a little bit about the energy of oscillations, which I'll call E. And you should know this, that energy equals kinetic energy plus the potential energy. Okay, so what is the kinetic energy? It is half mv squared. We all know that. And U, the potential energy, is defined to be the negative of the work done by the forces. The negative of the work done. Work done is the integral of f dot dx, right? So this is our energy. So what does this simplify to? This becomes I'll bring the m inside. M over 2 times v squared. V is this, so I'll have to square that. Actually, I'll keep it. Okay, half m times v squared. So v squared is a squared omega squared cosine squared of omega t plus phi. Okay, that is a bit congested. Okay, so I'll just rewrite this here. So the energy equals half m a squared omega squared cosine squared omega t plus phi minus, now F equals ma, right? I can bring the m out, so I get minus of m times the integral of a dx, a dot dx. So I'll just rewrite this term here. This term is m times the integral of, we know that a equals minus omega squared x, right? We assume this and we derived all these expressions on the left. So this is the case, and so this becomes minus omega squared x dx, which can be written as omega squared is a constant, so that is minus m omega squared times the integral of x dx, which simplifies to being equal to minus half m omega squared x squared. So let's substitute that here. So I'll get this is equal to half m a squared omega squared cosine squared omega t plus phi. There's a minus here, right? There's a minus here and there's a minus there, so it cancels out. So I get plus what is that? Half m a squared omega squared x squared. Oh, sorry, there's no a squared. Half m omega squared x squared. So where do we get with this? So this is half m a squared omega squared cosine squared of omega t plus phi plus x is this, right? A sine of omega t plus phi, right there. So plus half m omega squared times a squared sine squared of omega t plus phi, right? Okay, so we can take something in common here. So this is half m a squared omega squared can be taken in common. So inside we get cosine squared of omega t plus phi plus sine squared of omega t plus phi. See something? Yes. This term, whole term is 1. This is just 1. Sine squared plus cosine squared is 1. So we get that it is equal to half m a squared omega squared, and this was all equal to E, which is the energy of oscillations. And so you can see that this whole term, this whole thing here is a constant, right? There is no dependency on time here. So the energy of oscillations is a constant. So that is nice, because there is no energy change. So we can also use this in a lot of things. So yeah, this is the energy of oscillations. Again, I'll review this. Energy is kinetic energy plus potential energy. Kinetic is half mv squared. Potential is defined as negative of integral of the work done. Negative of work done, which is integral of f dot dx. And we simplified this, and we get that the total energy is a constant. So you might be asked to find the energy, etc. So this is kind of a nice thing to know. We'll do some problems based on so far what we have done. So yeah, I'll see you in the next video.